DC, what it is, this lump here actually goes positive, so you get these lumps of voltage. So if you were just watching it on the output of the rectifier, you will see a voltage going up and down at a frequency. So this frequency is the frequency at which the thing is being rotated, depending on how many poles it's got. So you get this voltage here. Now, if you put some kind of smoothing or some kind of capacitor or battery on it, we get this constant voltage. So that's just to give you a background of what rectification from AC to DC does. You generally drop a little bit of power in one of those, so yeah, it's something to think about, but it's pretty easy to do.
Do you have power losses in the capacitor stage? If you, how efficient is a capacitor?
Capacitors are pretty efficient to put energy in and pull it out again. There are some small resistive losses depending on how close it is. The problem with them is that over time they will degrade and eventually kind of fail, short circuit. In power electronics, the least reliable aspect of it are capacitors. So in photovoltaic inverters, the problem that they have is with capacitors failing. That's the first thing that will go. Generally in lifetimes when they're switching quite fast of 2 to 5 years, something like that.
Why does the system voltage, why does the battery stick the system voltage at a constant value?
The battery can absorb current and supply current. So what it will do, when the voltage is higher than the battery voltage, you'll get a blip of current pushing into the battery, and then you get another blip of current. Only at a time when the output from the rectifier is higher than the battery voltage, otherwise you won't get any current flowing. But that blip keeps it, pushes energy into the battery or capacitor can absorb it. There are some losses with it. A battery, it's difficult to talk about efficiencies because you also need to talk about how long you want to store that energy for. But generally we talk about you only will get back about 85% of the energy you put into a battery back from the battery. Right. Too much into that. So the most important factor in a DC-based system is the system voltage. So in an AC system, you need to look at voltage and frequency. In this system, DC voltage. It affects, as I was talking before, 100 amps. So we had a low voltage system, we had 100 amps flowing. If we had a higher voltage, we have a much lower current, and we know that power or resistive losses are related to current squared. So doubling our voltage will halve our current, which will reduce our power losses by a factor of 4. So actually, it's even better to increase our voltage. It will affect a lot of things: the cost of the cable, the cost of the rectifier, but it does affect the availability of components which are rated at that voltage. So 12 volt stuff is pretty easy to find because we use it in cars, whereas 48 volt stuff is pretty difficult to find because not many people use it much. So energy storage, been talking a bit about energy storage. Generally, I'm talking about the lead acid battery. I would say 99% of renewable energy-based standalone power supply systems, that's a made-up number, but anyway, use lead acid batteries as energy storage. So you've got a lead acid battery on your table. It's an electrochemical reaction. So you are converting, there is a chemical reaction going on when you put electricity through it. They're pretty cheap, they're easily obtainable. You can get them in most places. These were locally made Filipino batteries. This was a photovoltaic recharging station with a whole assortment of batteries: motorcycle battery, car battery, truck battery, deep cycle battery.
You can have all of those connected to the same system?
No, they, yeah, I'll talk about problems with this. This is not a very good example of how you do it, but he has 2 batteries here on the same system. It's not going to work very well. It's not a very good thing to do. Also, yeah, it's just, there are issues with the system, but that's how we're doing it, and that's how it's working. But, so, when you're doing a design, you need to size your battery bank correctly so that it can store enough energy so that when you don't have your resource, your wind or your solar, that you've actually got enough energy stored in the battery to cope with that. So it's a mixture of knowing how much load you need, what's your load requirement, how much energy you're getting in from your renewable energy, and how long you want your system to work without any energy input. So you're coping with variations in supply and demand, and there are two different methods here. Won't go into them too deeply. You either use a number of days of autonomy, which basically you say that this system will work for 4 days or whatever with no energy coming in, and it will supply the loads, and that's how you design your battery bank. And that's how I would do a system. I would say typically 4 days, no input, and that's how I would design how big a battery I need. Generally, that works. You may have times in winter where it doesn't work, times in summer when you're wasting a lot of power, but you also need to take into account the maximum current capacity, and your battery bank capacity should be more than 8 times the maximum current that goes into or out of the battery. If you want to know more, we'll talk about that more. Talk to me later, it's probably not particularly. I could go on about problems with lead-acid batteries. They're the weak point in most off-grid renewable energy systems. They self-discharge at a rate of 1 to 5% of total energy per week. They're affected by temperature, both its capacity, how much energy is stored in there. If you've got it at 25 degrees, there's more energy? Less energy, more energy, can't remember, in there than at cooler temperatures. And their lifetime is affected by that. Capacity depends on the current. If you draw 1,000 amps from a battery, it won't last very long. If you draw 1 amp from a battery, it will last for a very long time. So it depends upon the current you take of it. Lifetime is dependent upon how many times you charge it up and discharge it, and also how far you discharge it. So you can take it all the way down to 0 and back up to 100, but you can only do that, say, 50 times, whereas if you take it down to just to 80% and back up to 100, you could do that a lot more times, thousands of times. They're very heavy, so storage density is not very good. That you need to, with open-vented lead-acid batteries, not with these sealed ones, but you need to equalise them, so make sure that all the cells are the same voltage. And they cost around £40 per kilowatt hour, and they've been around for about 100 years. There's not much chance of the cost coming down dramatically. But they are very obtainable. They're easy to obtain in lots of places. If possible, well, firstly you should use deep cycle batteries. That's a kind of, you have to use, otherwise car batteries will fail in very quickly. They're not designed for pushing energy in and pulling it out many times. If possible, don't use them. So the water pumping system I showed, that doesn't have any batteries in it. And it's storing water, it's storing energy in the form of pumped water, and that's a much more reliable system. We could do this practical. You've got your load, so the loads that we were talking about before, and you've got your solar panels on your tables. So what I want you to do is to design a battery bank to power the load that you have on your table with the solar panel that you have on your table. The load is going to be run for 8 hours a day, and it's based in a place in Ethiopia. That's where my brother is at the moment, that's why I've chosen it. And the solar resource varies from 5.4 sun hours to 6.8 sun hours per day. So the first thing we need to do is figure out 8 hours per day, how much energy do we need? Okay, so if you can all do that, I think you've got enough data for that. Yay!
See what the rating of that.
5 watts.